Zoom recording. Okay, now we're recording and let's get started. Can you guys see the PowerPoint?
Yes.
All right, perfect. Thank you. And let's get started for chapter 8. You will have a third test after chapter third midterm. Then we're down for all the midterms. Okay, and in chapter 8, we will talk about solutions. So the first part of the chapter will come up what is a solution? What is the property of a solution? And then the second part, we will talk about calculations regarding the concentration of a solution. So first, let's take a look, and this is the guideline for the whole chapter. And first, let's take a look, what is a solution? Before we study solution, let's take a review something we learned in very early of this class, chapter 1. We studied matter can be classified into two types, a pure substance and mixture. If you guys remember, matters in chapter 1, pure substance, mixture. And this chapter, we study mixture. And we know mixture by the appearance of the mixture. We can further divide into two types, homogeneous and heterogeneous. Do you guys remember that, guys? Everyone?
I remember.
Okay, can you give me an example of each? A homogeneous mixture and a heterogeneous example of each.
A heterogeneous mixture would be like if you had a glass of iced tea, you'd have the liquid phase, and then you might have ice cubes, you might have leaves in it, so there would be several different phases.
Good.
And then
That's a heterogeneous. Yes.
And then a homogeneous mixture would be like if you dissolved salt in water, there would just be one liquid phase.
When after the salt dissolves, right? Good. Yes. Very good. Now, if you guys all understand what is a homogeneous mixture and what is a heterogeneous mixture, then you know what is a solution, because solution is a homogeneous mixture. Now we don't call it a homogeneous mixture anymore, but we call it a solution. But essentially, a solution is a homogeneous mixture. Two or more substances, with each substances retaining its own chemical identity mixing together. What does it mean? Meaning when you mix these substances, they do not have chemical reaction between them. You're physically mixing them. That's the definition of a mixture. If they're happening to a reaction, then there's not a mixture, it's a reaction. So no matter how many substances are mixing together, you see one phase, and the components of the mixture do not react with each other. They will retain their own chemical identity. That is what a solution is. And of course, solution is a homogeneous mixture, but its chapter, we give it a new name, solution. In a solution, because we have multiple components, so we have a definition for these components. We have names for these components. The one that exists in major amount, is called the solvent. The others that exist in minor amount relatively are called a solute or solutes, depends on how many components you have. Again, the one exists in major amount is called the solvent. The others are called solutes in minor amounts because they are different amounts. Sometimes you have to dig, oh, hey, what about 50-50? In that case, you can call either one. There's no really strict rule on that. But one thing to keep in mind, if water is one of the components, we assume water is always the solvent. Water is always the solvent, such as water. Again, even though water may be sometimes, most times it won't. If water is a component of a solution, we assume water is the solvent. And if that's the case, we call the solution, we have a new name, aqueous solution. Aqueous, AQ, yes, AQUEOUS. Okay, aqueous solution. Questions, guys? If no, I'll give you a couple of minutes, take a look at the properties of a solution. Some of them have talked already, some of them may be new, but should be very easy to understand. Please take 1 minute or two, read these 5 properties. Again, these are kind of like give you a general picture of a solution, not really a property, but a general picture of what a solution may look like. Okay, give you a couple of minutes, and please let me know if you have any questions regarding these 6 statements of a solution.
I have a question.
Yes.
Do you expound a little more on the number 2 has a variable composition?
Yes, good question. I will. I actually, if you didn't ask, I'll still reply. This is one of the most important property for a mixture. As a matter of fact, the reason we define something a mixture is actually something has variable composition. What does it mean? For example, if you're making, let's say, coffee. Coffee is not technically a solution, but let's say we assume coffee is a solution. Even though you're buying that coffee from the same shop, made by the same coffee maker, using the same machine, 2 coffees won't be identical. Why? Because there is some variations between one batch and another, no matter how they follow the instructions. Maybe the first one has tiny bit more caffeine than the second one, or the first one has tiny bit of sugar in the second one. So that is called variable composition. That is different from pure substance. If I give you 2 cups of water, as long as they say, hey, these 2 cups are pure water, then I assume no matter which part, they should be identical because they're pure water. But mixture will be different. If I give you 1 cup of sugar water, another cup of sugar, there must be some difference between these 2 cups. Even though I said I made them identical, no way, because they are the property of mixtures. Does that make sense?
Yes, thank you.
That's what means variable composition, because one thing from another place, one guy from another guy, there will be a difference. Any others, guys, regarding the general properties? Kind of give you a picture of what a solution is. Again, solution is a mixture. It's a homogeneous mixture. That's why you see this statement. These particles are uniformly distributed through the solution. They will not settle, no matter how long you put it there. But the components can be separated by physical means. Why? Because they're physically combining together. They're not reacting with each other. So if I have a chance, have a way to separate them, in the end, I can get the components back if I have a way. So these are the general pictures of a solution. And to give you a better picture, there are 2 other types of mixtures for you to compare, for you to have a better idea. One type is, like we said earlier, a heterogeneous mixture, and sometimes we call it a suspension. The difference between suspension and solution is in a suspension, the particles are too big. They cannot be uniformly distributed in the whole solution. They will settle because they're heavy, they're big. And that's what we call a heterogeneous mixture. Now, suspension particles are big, they will settle. Solutions, particles are small. They're either molecules, atoms, or ions. They evenly distributed, they uniformly distributed, they're tiny. But between solution and suspension, the smallest tiny one and the big one that will settle, there's something intermediate. Something intermediate means in a certain type of mixture, the particles are bigger than solution, but they're not so big. Again, a few types of mixtures, their particles are bigger than solutions, but they're not so big so that gravity will pull it down. And we call those mixtures between suspension and solution a colloidal dispersion or colloid. Okay, colloid. C-O-L-L-O-I-D. C-O-L-L-O-I-D, a colloid. A colloid is something between a solution and a suspension. Again, the particles are bigger. They are still uniformly distributed, but they're not like solution, mostly clear. And also, they're not like suspension, the particles will not settle. And an example you guys have with you about a colloid is the milk you drink every day. The milk you drink every day, no matter what type of milk, are not solutions. The particles in the milk, mostly proteins or lipids, are bigger than small molecules. So normally milks are not clear, but the proteins are not settling unless the milk has gone bad. So milk is an example of a colloid. Now, sometimes, how can we tell whether we're having a solution or colloid? There's a very famous experiment. You can do it at home. If I have two things, sometimes I couldn't tell. Suspension, you can definitely tell because they're settled. If you cannot tell between a solution and a colloid, you can use a laser or a flashlight. Let the light pass through both. If you see a path of light, like here, sorry, like this, if you see the light have a path, then that's a colloid. If you don't, the light all scattered away like this, then that's a solution. And that experiment is called a Tyndall effect. Tyndall effect is unique for colloid. Only colloid will have that path of light. Why? Because the particles of a colloid are bigger. They can scatter light so that you have a creation of light of path. So you can do an experiment at home. Solution will not give you that path of light, but colloid will. And also, if you wake up in a moist woods in the morning, you see the sunlight path through, you see the beam of light, that is also a Tyndall effect because those tiny droplets of water actually are suspended in the air. So in the morning, the moisture air is a colloid, not a solution, because the water droplets are bigger than little molecules. Okay, so these are examples of what a solution and what is a colloid. We don't talk more much of a colloid, as long as you know what is a colloid. And you have a better idea what a solution is. Okay, of course, we focus most on solutions. Any questions, guys? Any questions so far? Okay, next. Because solution is a mixture, so how much solute, again, solute is the one in minor amount, can be dissolved in a given amount of solvent. What is solvent? The one in bigger amount. Under a given set of conditions. So under a certain condition, how much the solute can be put into the given amount of solvent is called solubility of that solute. Okay, the solubility of that solute. Basically, it's a qualitative term. How much solute can I add to be dissolved in a certain amount of solvent? Of course, you have to set the condition. You have to set the amount of solvent because more solvent, of course, everybody know more solvent can accommodate more solute. So we have to know how much solvent we're talking about and what is the condition we're talking about. Now, how much solvent we know, again, we always know more solvent, more solute. That's, we don't even need to talk. What are the conditions? The first condition is temperature. For solids, their solubility in water will increase. Now here, water is a what, guys? Water is a what?
A solute?
What? Water is a what?
And I'm having trouble hearing you.
I'm sorry, can you guys hear me now?
Yes.
Water is a what?
It is a solute, or can be.
Take a look. We said earlier, if water is one of the components, always a what? A
Solvent.
A solvent. Okay, water is solvent. For solids, when you dissolve them in water, their solubility will always increase. For most solids, not 100%, will increase as the temperature increases. Again, for solids, if the solutes are solid, before you dissolve them, if they're solids, their solubility increases as the temperature increases. Higher temperature, you dissolve more. You guys have the idea, you can try it. As a matter of fact, for you guys, if you have made iced tea when you go to work in a fast food store, you know how to make iced tea. You have to heat really hard in order to put the sugar in. Why? Because higher temperature, the solubility will be higher. But the trend is different for gas. The solubility of gas will decrease if you increase the temperature. Okay, increase the temperature. You guys have the idea too. I mean, your Coke, think about it. Does the Coke has more gas when it's cold or hot? Think about it. You memorize the trend. Next is pressure. Pressure has little effect on gas or liquid if we're talking about solid. Pressure has a major effect on gas, meaning higher pressure, more gas can be dissolved in. Why you always talk about water? Because water is the most commonly solvent around us in nature, and it's the most commonly seen solvent in this chapter for us. Why? Because water is the most common solvent. We're a planet water. Even we're made by water. 70% of us is water. So that's why we talk about water most. Again, guys, first know what is solubility. I give you a certain amount of solvent and then set a given set of condition. How much solute can be dissolved? That's called solubility. The amount of solvent, again, it's easier to understand because more solvent, more solute can accommodate. A cup of glass of water, a bucket of water, of course, the bucket can hold more sugar in it. That's easy to understand, but what are the conditions? Please know these conditions. For solids, if the solutes are solid, temperature increases, solubility increases. If the solutes are gas, the trend is opposite. Pressure has little effect on solid or liquid, but higher pressure will dissolve in more gas. And also you can use that soda as the example. Once you open the bottle of soda, what happens? Gas cup pops out. Why? Because you open the soda, the pressure is released. Lower pressure, lower solubility. Higher pressure, higher solubility. Does it make sense, guys? All these concepts. And first of all, of course, all of you must know what we're talking about. What are solutes? What are solvent? And what is water? Water is always the solvent. If we're talking about water is the component. Any questions, guys? Okay, I'll ask one of you to repeat something for me. Alan, can you tell me what is the solubility trend for solids?
The solubility goes up as the temperature increases.
Very good. Now take a look at the table. Do you see that trend? There give you a few solids. They're all ionic compounds. Take a look. Do you see that trend? Higher temperature, solubility increases.
Yes.
You guys see that, all of you? Take a look.
Yes.
What's solubility? Grams of solute per 100 grams of water. Why I have to say 100 grams? Because I have to tell people how much solvent do I have. If I have 200 grams of water, then I can dissolve double. So I have to tell people, if we want to talk about solubility, I have to tell people how much solvent are we talking about? Because more solvent can hold more solute. And if I set 100 grams of water, good, then we talk about temperature. You can see that for most solids, again, there are exceptions, but for most of us, most solids here, you can see this table. These ionic compounds are solids. Their solubility increases as you increase the temperature. Of course, some are lower, some are higher, but the trend is the same. Okay, the trend is the same. Next, when a solution contains the maximum amount of solute that can be dissolved under that condition. When the solution contains the maximum amount of the solute that can be dissolved under the set condition, we call the solution the saturated solution. Saturated, you guys know what saturated means, satisfied. They dissolve the maximum amount. So let's take a look. Let's use the table we just seen, take a look. For example, I have 100 grams of water. At 50 degrees Celsius, I have 2 grams of this guy. 100 grams of water and 50 degrees Celsius, this guy can only be dissolved to what? 1.94 grams. Now I have 2 grams in it. What does it mean? Means this guy dissolves what? This solution has what? Maximum, actually more than maximum. So the resulting solution will be called a what? Saturated solution. Does it make sense, guys?
Yes.
Everyone? Now, question for Millie. Still using this example, I said at 50 degrees, 100 grams of water, instead of have 1.94 grams of this lead to bromide, I have 2 grams of it. What will happen? What would you see?
It wouldn't completely dissolve.
It won't completely dissolve. Means what? Because we have 2. The maximum can dissolve what? 1.94. So that means what? The extra will remain in the solution as a what? As a solid, because you cannot dissolve all of it. And this is what happens shown here. The dissolving is still happening. What does it mean? It means the solid is actually dissolving, but in the meantime, the ones in solution were actually coming back and forth. But the amount of here will not change. How much? 0.06 grams. Somebody's confused. Well, what the heck is 0.6 from? I said earlier, I have 2 grams. This guy only can take 1.94. So the difference is what? 0.06. That amount will never change unless you increase temperature. If we're talking about 50 degrees, you will always have 0.06 grams in there. But the process is still going on. Okay, they're back and forth. That's what we call equilibrium. Okay, that's always chemistry that nature does. The process doesn't stop. The particles here is still going into the solution, but meanwhile, the solution particles will come back. Why? Because the solution has maximum. So the solution here is called a saturated solution. Does it make sense, guys? Everyone?
I have a question. In the last
Yes.
chapter, when you were talking about vapor pressure, at one point you referred, I think you said, well, I know with that one there's the equilibrium, but I think you called
Yes.
it dynamic equilibrium once.
Yes.
Okay, so it can be dynamic equilibrium with both solutions and solutes and vapor pressure?
Yes. As a matter of fact, in chemistry, in nature, most of the processes are actually dynamic equilibrium.
Okay, thank you.
The process doesn't stop. They're just reached a certain point. The macroscopically, you don't see a change, such as here. You always see 0.06 grams here, but That 0.6 gram is keeping changing. Something is going back, going off, something is coming back. So that 0.0 won't stay the same, but the amount is always 0.06. That's what we call dynamic. Dynamic means what? They're always moving back and forth. Yes. Now, by the way, if somebody in the future, you guys, maybe some of you in the field of this, if I ask you, hey, can you prepare a saturated solution for me? How do? You check the solubility, add more than that. Bam, you get the bottom. As long as you see something never dissolves, no matter how well you shake it, as long as the temperature doesn't change. Then you always see something in the bottom as solid. That means what? You got a saturated solution, such as go ahead and make some sugar water. Keep adding sugar until a certain point, no matter how much you keep adding, the sugar won't go away. The sugar will always stay in there. That means you got a saturated solution. This is how you prepare a saturated. Very easy. Just keep adding. No brain, but don't do much, little by little. Now, there is some exceptions, not exceptions, some weird scenarios in which a solution can hold more than it's supposed to hold. But I said that's a weird situation because that's an unstable state. So that's temporary. Sometimes a solution, maybe we do some trick, a solution may be able to hold more than it could hold. If that's the case, we have a solution called supersaturated solution. Supersaturated solution. Supersaturated means you eat more than you could eat. But that's not permanent, that's temporary. Temporary means no matter how you tiny bit agitate that solution, or even put your finger in it, put your pen tip in it, or drop a dust mite in it, that will cause the extra to come out as solid. Like this, very beautiful. Okay, very beautiful. This is a saturated solution. See, this guy dropped a tiny bit of whatever that is, maybe the same solid into it. Boom, right away, everything comes out. Of course, the extra comes out. You will see a solution like this. So basically, a supersaturated will go back to saturated if disturbed. Okay, that's what we call this as the unstable state. Does it make sense, guys? It's not same. You won't see that often, but it does exist, supersaturated.
How do you get it into a supersaturated state?
Mostly we dissolve more and then lower temperature. And if we lower it carefully, it won't, because we know temperature lower, something's supposed to come out, but sometimes it doesn't come out. So that's kind of where we get a supersaturated. Most times we do that. Any questions, guys? Now, question for one of you, Kaylin. We have talked about saturated solution. We talk about supersaturated solution. Let's go back to this example again, the one I put a circle there. Let's say under 50 degrees, 100 grams of water, I only have 1 grams of solute dissolved. What do you think that solution is called? Can you guess? What do you think that solution is called, Kaylin? If I have only 1 grams in dissolved in there.
I don't know.
You know, think about saturated, supersaturated. If I only have 1 means not enough. Anybody can guess what is it called?
Unsaturated.
Unsaturated solution. Very good. Okay, so we have 3 types of solution. Okay, even though I didn't put it here. If you have more than you could dissolve, if you have solid remains in there, the maximum, saturated. If you don't have enough, means the solution will be clear. Less than the maximum, that's called unsaturated. If you dissolve more than you could, but that's unstable state. We call that supersaturated. So mostly we'll see 3 types. Supersaturated is not common, and saturated, how can we know? If we have a solid remains, that's a saturated. If the solution is clear, could be either saturated or unsaturated, depends how much in there. And we have to further test. All right, that's these 3 types of solutions. Now, here are 3 factors, 3 methods when we try to dissolve something. For example, if you want to dissolve sugar or salt in solution, here are 3 methods or factors that can help to improve the dissolve, how fast the thing can be dissolved. The first one is increase the subdivision of the solids, means make it finer. Instead of dissolving granular sugar, you can dissolve sugar powder. Powder will dissolve faster. Why? Because powder is finer. The surface area of sugar powder is bigger. So the contact of sugar powder with the solute water is bigger. So dissolve will be faster. That's the first factor. Again, called method. How can we, if we want, how can we dissolve things faster? Is increase the subdivision. Subdivision means what? Make it smaller, make it check. So that means if you dissolve a big chunk of sugar, it's gonna be slow. If you dissolve sugar powder, it will be faster. Number 2, the degree of agitation. Agitation means what? You use your finger to stir, or use a stick to stir, or swirl. Agitation will what? Help dissolve because increase the contact. Number 3, increase temperature. Like again, use the example if some of you working in Walmart, it's not Walmart, McDonald's, somewhere, the fast food store, if you have made iced tea, if you want to dissolve faster, what would you do? Heat the tea, hot tea. Why? Because temperature increases, the kinetic energy of these particles will be bigger. They will dissolve faster, they move faster. So these are 3 factors help you to make a solution. Finer solute, agitation, swirling, or temperature. Questions, guys? Okay, next, let's talk about a very important topic. Is previously we talked about how fast can we make it dissolve, but the first question to answer is whether A will dissolve in B. They never could dissolve, no matter how agitated. You think about it, if mix oil and water, no matter how agitated, you soil your arm, you won't dissolve these 2. Why? Because they don't even dissolve. So the first most important so far, besides understanding everything about solution, is how can we tell a substance will dissolve in another one? In this topic, we have 2 subtopics. The first one is most substances, their solubility. Again, what is solubility? Solubility is how much solute can dissolve in a certain amount of solvent under certain condition. Just whether or not they could dissolve, or how much they can dissolve, is determined by a rule. This rule is called empirical rule because it's summarized by experience, called like dissolves like. Like dissolves like means if the polarity of 2 substances are similar, they tend to dissolve with each other. More similar, dissolve more. If the polarity of 2 substances are different, one polar, one nonpolar, then the solubility will be low or never dissolve at all. That is what like dissolves like means. Again, most substance, especially when we're talking about gas in liquid, liquid in liquid, and some solid in liquid solution. You can see most cases, this rule works very good. Even though we're not making a solution yet, I can tell as long as I know the polarity of A and B. Again, if A and B polarity is similar, means both polar or both nonpolar. They're similar. They tend to dissolve with each other. If they are different, they don't dissolve with each other. For example, water, like I said, we know water is the most commonly solvent we experience every day. Our planet is a water, it's full of water. Can anybody tell me, let me ask one of you. You have done this even in your test. Becca, can you tell me whether water is a polar solvent or non-polar solvent? Becca? Hello, Becca?
Yeah, I'm sorry, my mic wasn't working. It's polar.
Polar, very good. Guys, you have done this, right? Water is what? It's bent. So it's polar. The shape is bent, of course. Water is polar. Very good. Water is actually the most commonly used polar solvent in our daily lives. Now, still you, Becca, so don't mute it. We know water doesn't dissolve with oil. Can you guess oil is polar or non-polar?
Non-polar.
Polar. Why? Because what? They don't like each other. We know they don't dissolve. Why they don't dissolve? Because they don't like it. We can like dissolves like. If they don't dissolve, they don't like. What doesn't like mean? Means water. If water is polar, we know the oil is what? That's why they don't dissolve. Very good. Thank you. Now, because water is non-polar, so if I want to make oil dissolves, I need to find something non-polar. Anybody give me an example of non-polar solvent in your daily life? I don't want to give you fancy ones. In your daily life, which solvent do you think is non-polar? Anybody?
I have no idea.
Anybody? Again, you use that every day.
What was the question again?
Oil doesn't dissolve in water. We know oil is a non-polar. So if I want to dissolve oil, something non-polar as well, because like dissolves like. So my question is, can any one of you give me an example of a non-polar solvent? I told you, you guys use that every day. I'm not like asking you from nowhere. Anyone? No? Okay, now I'll tell you. Gasoline is a non-polar solvent. Gasoline is a mixture, but overall it's non-polar. Even though some of our gasoline has 10% of alcohol, alcohol is polar, but gasoline, most of it is non-polar. Because gasoline is non-polar, next time you guys can try. Again, don't try too big amount. You can try a tiny amount. See if gasoline will dissolve oil. They will beautifully dissolve. Okay, beautifully dissolve. So this is the first rule. Again, very easy to understand, guys, right? Polar dissolves polar, guys. Non-polar dissolves non-polar, guys. Dissolves non-polar, guys. That's like dissolves like. Like we said, it applies for most cases, except in one case. Solid in liquid, in which the solid is an ionic compound. That rule doesn't work well. Again, it applies to most things. Even solid in liquid, it works. But if the solid dissolves in liquid is an ionic compound, if the solid is an ionic compound here, then the rule does not work well. That's why we say here, in most cases, it works. And for solid in liquid solution, in which the solid is not an ionic compound, it works. But if the solid is an ionic compound, this rule does not work well. That's why we call this rule empirical rule, because it works from experience. So our experience is if the solid is an ion compound, a rule doesn't work well. We have to use a different rule. So what is the different rule? If we have ionic compound, Again, you guys are very lucky because you don't have to memorize it. For most one-on-one students before, they all have to memorize the rules. It's a very difficult rules to memorize, but you guys are lucky, you can use it. But I still need to tell you what is the rules for ionic compound. Ionic compound, hope you guys still remember what is ionic? Metal, non-metal, or metal and polyatomic. Basically, you have a positive ion, you have a negative ion. You guys remember we didn't do the formula cross. So I just try to bring guys memory about ionic compounds. Okay, you have metal and something negative. The negative can be a non-metal or can be a polyatomic negative. You get the formula. These are ionic compounds. So here, this is the rule talking about how do we determine whether an ionic compound dissolves in water or not. Like dissolves like it doesn't work well for ionic compound in water. So we have to know whether an ionic compound dissolves in water using this rules. This rule has two parts. The first part dealing with soluble ionic compound, with some exceptions. The second rule deals with insoluble compound, with some exceptions. So that's why we have two parts. Let's take a look at the first part and how do we use the rule. Part one, again, take a look at the title. Soluble compound, meaning most of the compounds in rule one are soluble. They will dissolve in water. There are some exceptions. Exception means sometimes they don't. Most times they do, but sometimes they don't. Some exceptions. So let's take a look. If your ionic compound contains nitrate, acetate, lithium, sodium, potassium, ammonium, guys, 6. Look, nitrate, acetate, lithium, sodium, potassium. If the ionic contains any one of these 6 in their formula, the ionic compound will be soluble in water. No exception. Does it make sense what I said? Guys, I told you you can use the rule. You have to, you can look at the notes, it's fine, but you have to understand how. Does it make sense, guys? If the formula contains any one of those 6 ions, compound will be soluble in water. The rule are used to determine whether something dissolves in water. So you look at the formula. Does the formula contain any of these 6? If it does, soluble, no exception. So we're done for here, these 2 guys. Let's take a look at this guy. If the formula contains chlorine, bromine, and iodine, halides, chloride, bromide, iodide. Again, we're talking about ionic compound. That's why we have a negative charge for this one. They're -1. These guys will generally be soluble unless the metal is lead, silver, or mercury. Take a look. These guys are soluble except combining with lead, silver, or mercury. If that's the case, they're not. Otherwise, they are. Does it make sense, guys? Make sense, guys?
Yes.
Next, sulfates, SO42 minus. Sodium sulfate, potassium sulfate, barium sulfate, anything. They are generally soluble, except with strontium, barium, lead, and mercury. Among these 4, these 3 are group 2 metals. Okay, these 3 are group 2 metals. So basically, sulfate are soluble, except the other guy is group 2 metal, except magnesium. Magnesium is not in here. group 2 metal, and mercury. If that's the case, they're not soluble. Sometimes you guys, I'm pretty sure some of you are confused. Let's give you a couple of examples. Again, we're talking about rule number 1. Let's say sulfate. If I have sodium sulfate, can anybody tell me if it's soluble or not? Soluble or not?
I think it is.
Why? Because it contains what? Sodium. Okay, that's the reason. Of course, you can say sulfate, but the easy way is to look at it, sodium sulfate. Why? It contains sodium. We said anything contains sodium, it's soluble, no exception. How about ASO4?
Say it again.
ASO4 here, barium sulfate, is that soluble or not?
No,
No, why?
because sulfates aren't soluble with barium or the
Very
cement.
good. Sulfate is not it's with barium. So BaSO4 is not soluble. Let's take another example, 2. Now I'll move on, okay? Let me erase this guy. Silver nitrate, is that soluble? Silver nitrate, is that soluble?
No.
No?
Yes, because
Yeah.
it is,
Yes. Yes. Why? Maxon? Why?
because it has nitrate in it.
Nitrate in it. Nitrate is always soluble, no exception. So silver nitrate is soluble. How about silver chloride? Soluble?
No.
No. Why no?
Because it says the halides except those with silver, and chloride is a
Halides.
halide.
Halides are soluble, but silver is an exception. So silver halide, not soluble. Good. Okay, good. Guys, you will see a lot of questions in your test about this topic. Like I said, you are extremely lucky already. I know I shouldn't say that. I mean, chemistry is difficult after all, but I'm telling you, all students before are not using any notes when they take the test. They are memorizing the rules. Okay, all you do is practice so that you don't have to look at the rule until, I mean, if you look at the rule, you will spend more time on checking the notes. Okay, that's the part 1. We're talking about these guys are mostly soluble, but there are exceptions. Rule number 2. Things in here are generally not soluble. There are exceptions. Now, there are exceptions what? Something will make them soluble. So let's take a look. Carbonates, phosphates are generally not soluble. You see a carbonate or phosphate, your mind said, hey, this guy may not be soluble. That's your first mindset. Now you look at the other guy. The exception will be if they have alkali metals, ammonium. What are alkali metals? Lithium, sodium, potassium, they're alkali metals. Or ammonium, NH4. If that's the case, they're soluble. Why? Because we know lithium, sodium, potassium, ammonium are what? Are soluble in rule number 1. Of course, there are exceptions. Does it make sense, guys?
Yes.
Okay, number 2, hydroxides, minus, are not soluble. Except with alkali metals, again, with lithium, sodium, potassium, or with some group 2 metals, calcium, strontium, and barium. These are exceptions for hydroxides. Number 3, sulfides are not soluble, except with alkali metals, lithium, potassium, sodium, ammonium, and calcium. These are exceptions for sulfide. Otherwise, sulfides are not soluble. So you can see that Most exceptions for rule number 2 are actually what? Actually here. Why? Because they are soluble. They're always soluble. And there are some particular exceptions that you need to memorize. For example, hydroxides, besides sodium, lithium, potassium, and ammonium, you have calcium, sodium, and barium. Sulfite, besides sodium, lithium, potassium, ammonium, you have calcium and exceptions. But again, most exceptions for rule number 2 are here. Why? Again, because these guys are always soluble.
What
Okay.
makes the alkali metals soluble?
Alkali metal. I don't know. I said these rules are all empirical rules. That means we put them in water, we found them soluble. Okay,
Makes
and
them
if you right, I mean, if you really want to know the reason, in general is with alkali metals, the forces between the ions are not strong enough, so water can break them down. Okay, but there are more calculations. If you guys take Chem 111, Chem 112, you're actually calculating mathematically, quantitatively tell people how much they're soluble or not, actually. Again, the rules are the same. This is the picture from your book, but I found out the one I summarized is better. So either one we want to use, they're the same. These two are the same. Okay, if you feel, oh, hey, I like the one in the book, feel free. Okay, but this is kind of, I summarized in my way. You guys decide. So let's do a few practice quickly. Which of the following are soluble? Form a compound with lead. Very easy, guys. Which one? Which one will form a compound with lead that is soluble?
Sodium.
Which one?
Sodium.
Sodium? Sodium is a positive. Lead is positive. They can never form a compound.
Oh, my bad.
Right? Ionic must be a negative and a positive, remember. You have a positive already, so you're actually choosing from A through D. Which one? Guys?
Is it C?
C. Why C? Because what? Take a look, guys. All compounds containing what? Nitrates are what? Soluble. Okay, rule number 1. Nitrates are soluble. That's why you choose nitrate. The other ones are not soluble. Okay, lead sulfate, lead chloride, lead sulfite are all insoluble. Okay, see, again, guys, you will see many questions in the next test and the quiz. Okay, 10 questions, 12 questions. I'll ask each one of you quickly, give me an answer. Okay, you can check the notes. So first one, Caroline, lead chloride, soluble or not?
Not soluble.
Very good, no. Next, potassium hydroxide.
No.
Maxine, you're answering? Okay, Maxine, no?
Yes.
Think again.
My
It
answer
has
is
yes or no?
no.
No, okay, unfortunately you're wrong. It is yes, because it contains potassium. Anything with potassium is soluble. Okay, number 3, magnesium sulfate. Back up. Magnesium sulfate. Yes, sulfates are generally soluble, except with what? With sodium, lead, and barium. So yes, very good. Next, calcium carbonate, Alan.
No.
No, very good. Carbonates are not soluble, generally not soluble. Okay, next, mercury 1 chloride, gaseous. Devious?
Yes.
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 Yes. Unfortunately, answer is no. Chloride are generally soluble, but mercury is an exception. So no, not soluble. Okay, next, Millie, potassium sulfite.
Yes.
Yes, very good because of potassium. Next, lead acetate. Miss Grabby, I'm sorry, can you say your first name again? I still couldn't. I'm so sorry. I apologize.
It's all right. It's Carice.
Carice. Okay,
Yes.
Carice, right?
Yes.
Carice. Okay, sorry, so sorry. Carice. Next one, Carice. Lead acetate.
Yes, because it has acetate.
Yes. Very good, because of acetate. Next, who I haven't asked? Anybody? Olivia? Magnesium hydroxide? Olivia, magnesium hydroxide? Hello? Oh, she's not here. Okay. So is Kate here?
Yes.
Okay, Kate, can you say that? Magnesium hydroxide? No. Okay, magnesium hydroxide is a little tricky. It's slightly soluble, but I'll try to avoid that. But it's actually slightly soluble. I think it says here. Does it say here? Okay, magnesium hydroxide is slightly soluble. It's something between. So don't worry about magnesium. I'll try to, if I have that in a quiz, I'll try to correct that. Next one, Kate, barium sulfate. Barium sulfate. Kate.
Yes.
Yes.
Yeah.
Sulfate is
Yeah.
soluble with an exception of what? Take a look. Barium sulfate is soluble with except what?
Oh, so then no.
Barium. Okay, no. Next, ammonium carbonate. So anyone? I think I caught all your names. Ammonium carbonate. Guys, ammonium carbonate?
Yeah.
No.
Yes or no?
No.
No. Answer is yes. Why? Because ammonium, anything with ammonium is soluble, no exception. Okay, next, calcium chloride.
Yes.
Calcium chloride. Yes, chloride are soluble. Calcium is not an exception, so soluble. Last one, copper sulfide. Copper sulfide, guys?
No.
No. Okay, no, sulfides are not soluble, except with the alkali metals. Copper is not. All right, guys. I know in the beginning it's hard. You have to memorize. Trust me, try 20 compounds. Anything from the book, from my notes, cover the answer again, do it again. You can go back and forth for the notes. Why? As long as you understand why, do it 20 times. Explain to somebody else. Again, understand why. Explain to somebody else. 20. Trust me, you will find out, hey, I'm good. I understand this rule now. Okay, again, understand why each one is soluble or not soluble. You can explain. Then you, after 20 times, trust me, you will feel better about using the rules to determine whether an ionic compound or not. So far, we learned two ways of determining whether A will dissolve in B. The first one is like dissolves like. Sorry, like dissolves like. Like dissolves like means how close they're in their polarity. Number two is this rule, like dissolves like, does not work for ionic compound in water. Excuse me. Now, if it doesn't work for like dissolves like, we have a new empirical rule. Okay, empirical means these are from experience. Okay, these are things. Soluble basically means it will dissolve in a significant amount. Insoluble means mostly it's solid. There's no absolute thing, but those are from experience. All right, next. We'll start this topic a little bit, then we'll finish today. The second part of this chapter, okay, second part of this chapter is we want to deal with when we have a solution, how much solute present given amount of solution. So in a solution, how much solute is in there? Quantitatively, how much is in there? And we call that the concentration. You guys have seen concentration terms in your daily life a lot. Sometimes you say, hey, this is very concentrated, and that one is very diluted. That's talking about concentration. What does it mean? Means how much solute is present in a certain amount of solution. Some teas are very sweet. Some tea are less sweet. Means what? The very sweet tea is concentrated because of more sugar in it. The diluted tea means less sweet because less sugar in it. If we're talking about sugar, sweetness. So concentration describes one thing, and you're going to use that throughout this all calculation. Again, how much solute in a given amount of solution, not solvent, solution. Solution is the whole thing. Solute is that part. How much solute is present in a given amount of solution? Remember, solution is the whole thing, it's the mixture. So let's take a look. In this class, we will study two types of concentrations. Again, we want to how much quantitatively. That means we have to do the math. We will study two types of concentration. One type is called percent concentration. Another type is less commonly for you guys, maybe you have never heard of before, called molarity. So today I'll briefly introduce you percent and do one practice to give you an idea what concentration is before we complete it. The first percent concentration is called percent by mass. What is percent by mass? The mass of the solute divided by the mass of the solution times 100%. Take a look at the equation. Does it mean the same thing what I said earlier? What's concentration? How much solute is present in a given amount of solution? So given amount of solution is the mass of solution. How much solute is the mass of solute? Again, all the time, from now on, all the calculation in this chapter is related to that statement. Mass of the solute over mass of the solution is called the mass percentage or mass percent. Sometimes we use this symbol, M followed by percent means mass percent. Okay, mass percent. Or sometimes you will see mass over M, percent means mass percent. Either way, it means the same thing. Now, one thing we can know here is because solution is the mixture. What is the solution? Is solute plus solvent. That's how we mix them. So the mass of the solution, if we need it, can be calculated by adding the mass of the solute and the mass of the solvent together. You get the mass of the whole thing. But remember, you need to divide it by the mass of the whole thing if you want a mass percent. Does it make sense, guys? This equation?
Yes.
The calculation in this chapter is supposedly to be easy. Okay, calculation is to be very easy for chapter 8. Okay, please understand what is concentration. If you understand concentration, you don't have to memorize any of the equations because concentration is what? How much solute is present in a given amount of solution. Total, from the total, how much solid is over there? Mass solid over mass of solution is the mass percent. All right, let's take a look. The example. What is the percent by mass? I mean, mass percent. Concentration of glucose in a solution made by solving 5.5 grams of glucose in 78.2 grams of water. After you read the question, can you guys tell me what is the solvent, what is the solute, or what is the solution? Can you identify these two? You're only given two things basically. 5.5 grams of glucose, 78.2 grams of sugar, of water. Can you tell me which one is which? What is glucose? Guys, what is glucose?
It's the solute.
It's the solute. Good. What is water?
Solvent.
Good. You identify solute and solvent. So let's write down what is mass percent. Mass percent equals to what? Mass of the solute. I have it. Yes, 5.5 over what, guys? Mass of what?
Mass of the solvent.
What? Over mass of what? Solvent or solution?
Solvent. Sorry, solution.
Mass of solution. Remember, always the part over all. A given amount of solution, how much solute in there? So divided by mass of the solution, not solvent. Okay, not solvent. Times 100%. Plug in number, solute, 5.5 gram. Solution, solute, I have solvent, add them together. 5.5 plus 78.2 grams times 100. I got 5.5 plus 78.2, 83.7, 5.5 to 8.37 equals to 6.6%. Okay, 6.6%. Does it make sense, guys? Everyone? Please remember, I'm pretty sure some of you are gonna make the mistake. Do not divide by the solvent. All concentration is the amount of solute present in a given amount of solution. The bottom is always the whole thing, the solution, not just any component. The top is always the solvent, solute. Okay, again, remember, please, the bottom is always the whole thing. What is the whole thing? The solution is the whole thing. The mixture is the whole thing. How much solute over the amount of solution? Last question before we end today. Can you tell me, if I have a 10% solution, how can you give people an idea about the 10%? What that 10% mean? If I have a mass percent of 10%, means what? Anyone? How do we solve the question? If I even don't have the multiple choice, this is the multiple choice, it's easier. But if I don't, how do we solve the question? 10% mass percent.
The percent of the solute within the solution.
Yes. 10% means what? Percent means what?
Per 100.
Per 100. So 10% is per 100. So 10 over 100. So all we need to ask, what is that 10? 10 is what? Solute. 100 is what? Solution, right? Solute is 10 grams. Solution is 100 grams. That means what? Solvent is 90 grams because solution is the total. If one part is 10, the other part is what? 90. Answer is 8. Does it make sense, guys?
Yes.
Everyone, please. Okay, the first part of the chapter, the beginning of part 2 is I really want you to understand what a concentration means. No matter, we will learn 4 concentrations, 4 mathematical calculations, but they all mean the same thing. The amount of solute in a given amount of a solution, or we can say part per. Guys, you can write it down. What is the part? Solute is the part. What is all? Solution is the all. Always the case. No matter what concentration, what solution, what concentration we're talking about in the next lecture. Part per all. For example, part, see, mass over mass of all. Mass of part over mass of all. That's called mass percent. Okay, again, the unit for mass can be anything as long as the mass are consistent. Grams over grams, kilograms over kilograms, milligrams over milligrams, doesn't matter. Must be consistent. Okay, must be consistent. Some of you yesterday, I do remember, when you do the gas law, one of the volume is 500. And so is that 1 liter? Another one is 500 milliliter, I think. Some of you just use 1 liter directly with 500 milliliter, but end up getting the answer correct. I don't know how did you get it. Your calculate same throughout. I don't know, but keep in mind, if you want to use volume in chapter 7, volume has to be constant, except for ideal gas law. The same thing here. Mass must be the same unit. Doesn't matter what unit, as long as it's a mass unit. Any questions, guys? That's all for today. Any questions you want to ask? Okay, if not, I'll see you guys next Tuesday to complete chapter 8. Well, ahead of time, I'll tell you the arrangement about